Okay. Hi, everyone. Thanks, Zhicheng, for this introduction. And today I'm going to talk about quantum recursive programming, verification, and implementation. So today's talk will be based on the following two joint works with Mingsheng Yin. The first work is about the verification part, and the second is about the implementation part. And during the talk, please feel free to pose me anytime if you have any question or comments. Great. So let's start with the question, why we need quantum programming. So it's just like classical programming. If you are a quantum algorithm designer, you might want to design a quantum algorithm in a high-level quantum program. Then you will use a compiler that compiles this high-level quantum program to low-level quantum circuit that can be implemented on quantum hardware. So in this process, there are several goals we hope to achieve. The first is these high-level quantum programming languages provides you a convenient description of the quantum algorithms. And the second is the compilation process provides you an efficient implementation of these quantum programs. And of course, we want to do some verification. We want to verify the correctness of the quantum programs. We want to guarantee that it correctly reflects the target of the quantum algorithms. And we might also want to verify whether this compiler correctly compiles the program to the circuits. And in today's talk, for the verification part, I will only cover the verification of correctness of quantum programs. Great. So what we want to do is to tackle the quantum recursive programming. So for quantum recursion, we need two programming features. The first is recursion. And in our context, it refers to recursive procedure calls. It allows a static short program text to generate a dynamic long computation. So there are a lot of examples in classical computing of recursive programming. For example, we have the celebrated Horst-Quicksort algorithms. We have numerous recursive data structures that can be recursively programmed. And also we have the divide and conquer method in which many algorithms can be recursively programmed. The second feature for achieving the quantum recursion is quantum control flow. So it is essentially a superposition of program execution. Quantum control flow is typically guarded by the so-called quantum if statement. So here is an expression of the quantum if statement. You can think of it as a quantum version of the classical if then else statement. So here Q is a qubit, also known as a quantum coin. When Q is in state kit 0, we execute the program C0. And when Q is in state kit 1, we execute C1. But Q is a qubit, so it can be in the superposition state. For example, Q can be something like alpha kit 0 plus beta kit 1, where alpha and beta are complex amplitude. So in this case, C0 and C1 will be executed in superposition. And we can have another view at the Q statement that is writing out the unitary it describes. So this unitary is just a combination of controlled U0 and controlled U1, where each UI corresponds to the semantics of CI. That is the statement CI described. So what is quantum recursion? It is just a combination of these two programming features. And their interplay is powerful and intricate, as we will be seeing later. Let's start with a motivating example to show the power of quantum recursion. So this example is quantum Fourier transform, which is a very important subroutine in the quantum phase estimation algorithm and the celebrated Shor's algorithm. So quantum Fourier transform is the quantum version of the classical discrete Fourier transform. It will transform a computational basis J to its corresponding Fourier basis. The following is a textbook quantum circuit for QFT, and it is composed of 1 and 2 elementary quantum unitary gates. And as you can see, the size of this whole description depends on the number of qubits n. So when n grows very large, the size of this description also grows very large, and it will become very complicated for human to comprehend. Now, a natural question is whether we can have a more economic and elegant description of QFT. The answer is yes, by using the quantum recursive programming. So we can write QFT as a quantum recursive programs, which consist of 3 procedures. So each of these procedures is recursively defined. On the left-hand side, we have, for example, QFT is the name or procedure identifier of this procedure. And we have M and N. They are classical parameters, or also known as formal parameters of this procedure. On the right-hand side is a procedure body that defines this procedure. For example, in the QFT MN, we will call this procedure itself recursively with different classical parameters. Here, m plus 1 is different from m. And this QFT also calls other procedures, including the rod and shift, which are also recursively defined. So here you can see the recursive procedure calls. And here we also have the quantum control flows guided by the QIF statements. This QIF statement, it will create 2 quantum branches. And in each of the quantum branch, we will call the procedure rod itself with different parameters in 2 quantum branches. So you can see the interplay between quantum control flow and recursive procedure call. And it is easy to imagine that this interplay is actually complicated because you can go into 2 quantum branches in superposition, and in each of these quantum branch, you call the procedure itself recursively. And actually, there are many other examples of quantum algorithms that can be written as quantum recursive program. This includes the generation of several recursively defined quantum states, and also including the quantum state preparation, implementation of the quantum random access memory. If you have interest, you can find these examples in our papers. Okay. So now we are ready to have an introduction of the programming language that describes quantum recursive program. This language is called QC++, which is introduced in our first paper about verification of quantum recursive programs. So here is the syntax of this language, which roughly tells you how you write or construct these programs in QC++ using these building blocks. So a quantum recursive program can be written as a set of procedure declaration. So each of these procedure is just like what we have seen before. It consists of the name of this procedure, and U bar here is a list of classical variables, which are formal parameters for this procedure. And on the right-hand side of this arrow is a procedure body that defines this procedure, which is a statement. So what format can the statement be? So here we write a BNF form, which describes the building block for the statement. So C can be, a statement C can be a sequential composition of 2 statements. So that just means you first execute C1, then you execute C2. And C can be a classical assignment, which assigns a list of classical expressions T to a list of classical variables X bar. This is just like the classical programming. And here is quantum 1. A statement can be a unitary gate applied on a list of quantum variables Q bar. So it is slightly more general than the elementary unitary gate we consider in quantum circuits. And here we have the procedure call. So here P is a procedure defined in this set of procedure declaration, and T bar is called actual parameters. This is just like classical procedure call. So you just call the procedure with some actual parameters, and this will substitute these formal parameters by these expressions. And the procedure call can be recursive because the statement C that is the procedure call, can be on the procedure body that defines the same procedure P. So so in the procedure body, you can call the procedure itself. And we also have several classical statements, like the classical if then else statement. So it just have a Boolean condition B and if then else statement. And here is a while loop. You condition on B, and depending whether you want to repeat executing the statement C. And we also have these local classical variable block, which temporarily assigns the values of T bar to X bar within this block. And here is the quantum if statement as introduced before. So as you might note, we don't have measurement here. So this is because we want to have an easy and natural defined semantics for the quantum control flows. And if you introduce measurements, then the semantics will be very complicated. It is hard to define the quantum recursion. And this is typical for if you want your language to support quantum control flow. And if you want to describe a quantum algorithm with measurements, then you can use the standard techniques to defer all the measurements to the end of the quantum circuit. And then you only describe the unitary before these measurements. And I will also want to mention that here we allow classical variables, but they are only specified control of this program. So there is no measurement that measures a quantum variable and return this result to classical variable. We don't have this. The classical variables, you can use it in the parameters. As we have seen before, you can call a procedure QFT m+1. So you have a expression that computes m+1. And you can use these classical assignments to compute some intermediate results. And this result can be used in these parameters and used in this condition for if then else statement or while loop. And these classical variables are only classical in the eyes of the programmer. That means you might use a QIF statement to generate two quantum branches, and each of the branch might call another procedure. And that procedure might have, this different procedure might have different classical variables. Once they are put into the quantum branch, if you want to implement that, then they have to be implemented by quantum in the quantum way. Okay, so I will move on to tell you the operational semantics of RQC++ that roughly tells you how to interpret the syntax of the statement in the last page. So here we need to introduce a notion of configuration, which can be roughly thought of as the current state at some point during the execution of the program. So it is a triple where C is a remaining statement to be executed. And here sigma and psi, they are the current state of classical and quantum variables respectively. So the operational semantics of RQC++ will be defined as transitions between configurations. So you can think of it as a more formal way to describe the unitary transformation between states, because here we also have these remaining statements. So let's see some examples. Here we have a set of rules for defining the operational semantics. So the first is the simplest rule for the unitary gate statements. So if C is a unitary gate statement, then after one step of transition, the classical state is unchanged because it is a unitary gate. It only affects the quantum state. So the quantum state is updated from kit psi to another state. You just apply this unitary on psi. So that's simple. Here is a slightly more complicated one, the QIF rule for defining the semantics of quantum if statement. So here we have this horizontal line that separates the premises and conclusion. So that means if we have these premises above this line, then we can obtain the conclusion below this line. So it defines the semantics for the QIF statement. So suppose the current state psi, we can write it in the basis of the quantum coin. This Q, the quantum coin, we write it in this basis with amplitude alpha 0 and alpha 1. And if we have the transitions for each CI in these two quantum branches. That means if we know how to execute the different quantum branches, then we can combine them together into the semantics of, then we know how to execute the whole QuickS statement. And this is, you can suppose that each CI takes a classical state sigma and quantum state theta I. After several finite steps of transition, you terminate in the classical state sigma prime and quantum state theta I prime. Then you can combine these two executions into a larger one of the QuickS statement in superposition. So the subsystem that each CI axon will be entangled with this Q, the quantum coin. So this is just a more formal way to describe our previous unitary description of the QuickS statements. It is just a combination of two controls. And here we also note that C0 and C1, they will terminate in the same sigma I. They will terminate in the same classical state sigma prime. And this requirement is for the classical variables to be always disentangled from the quantum variables. That means classical variables always stay classical. And here we have this notation for finite steps of transition. So here star can be different K0 and K1 for different quantum branch, C0 and C1. So that roughly means C0 and C1 in these two quantum branch in superposition, they can take different number of steps to terminate. And this reveals the synchronization problem when you deal with the quantum control flow. So if you want to implement this QuickS statement and these two quantum branch, they have different numbers of steps to terminate. If you want to implement them together in superposition, then you have to synchronize these two quantum branches. And we will show how to automatically address this problem in the implementation part later. And here we also have this recursion rule for defining the semantics of a procedure call. So what does it mean to call a procedure PT bar? You just replace each of the formal parameters U bar by T bar within the block statement. Then you execute the procedure body C. And we also have this rule for defining the meaning of block statement. So a block statement here just means you temporarily assign the values of T bar to X bar. Then after executing C, you restore the old values of X bar. These two rules are exactly the same as classical procedure call and block statements. So the quantum one are here, these two rules. Okay, great. Now we are ready to get into some of the details of the verification and implementation. So the first part will be about the verification. In this part, I will talk about the correctness specification of a program in RQC++. This is by designing Hoare triple and defining their correctness. And using this specification of correctness, we propose a proof system with a set of proof rules to formally reasoning about the correctness of a quantum recursive program. And we further show that this proof system is sound and relatively complete. So the first question is how to specify the correctness of a quantum recursive program. The idea is by the standard Hoare logic. So, but we need to design the Hoare triple for this quantum recursive program. So a Hoare triple consists of 3 parts. The first and the third part are called pre and post condition, respectively. And in the middle part is a statement in RQC++. So this Hoare triple, if it is true, it roughly means when we start with some state that satisfies this precondition, Then after executing the statement or the program C, we will end in the state that satisfies the post condition. So this core triple can be used to specify the correctness of a program, or you can think of it, you can use it to specify what an algorithm does. So the condition will contain classical and quantum parts. The classical parts are just the first order logical formulas, which tells you something about the classical variables. For example, A can be x is larger than 7 and y is less than 0. So here x and y are classical variables. The quantum part tells you the condition that a quantum state should satisfy. So it is just the quantum states. The quantum variable should satisfy. So it is just the quantum state defined by classical variables. So for example, here phi can be defined by some classical variables I and n, where I is a bit array. It is just an array. Each of the cell is bit. And here n is an integer. And more precisely, it can be defined like this. It can be a computational basis specified by classical variables I and n. So it is just a classical array, I, indexed from 1 to n. Okay, so we have these Hoare triples. Now we can talk about the correctness of a Hoare triple. So here we can talk about the partial correctness of a Hoare triple. It roughly just it's just a more formal way of our previous intuition about whether a Hoare triple is true. So if so the condition is for any classical state sigma that satisfies the classical precondition A, and we have this transition from C sigma phi, they terminate in some classical state sigma prime per psi prime, then we have sigma prime satisfies the classical post condition B, and the quantum state per psi prime is equal to per psi in the classical state sigma prime. So this roughly means the classical state satisfies the quantum state satisfies the quantum post condition. And here we need this equality in some classical state, because remember, our quantum states can be defined by classical variables. So you need to assign values to these classical variables. So if this condition is satisfied, then we know this Hoare triple is true. And it roughly means you start some state that satisfy the precondition. After executing C, you satisfy this post condition. And we will denote its correctness by this notation. We might also consider the total correctness, which is just the partial correctness together with a termination condition that says this executing C always terminate. But in this talk, I will only focus on the partial correctness for simplicity. So here is an example of a Hoare triple for the previously mentioned quantum Fourier transform program. So here QFT-MN is the program we mentioned at the beginning in the introduction. And here, let's take a look at these pre and post conditions. So for the classical part, the classical pre and post condition is just m is less than or equal to n. So here mn are starting and ending indices of the quantum states. So this condition just says the number of qubits in the input states is positive. And for the quantum part, the input quantum states is specified by is a computational basis specified by the bit array J, which has indices from m to n. And as we know, the QFT the quantum Fourier transform just transform this computational basis to its corresponding Fourier basis. So here we have the post quantum state to be this per psi, which is quantum state defined by classical variables, J, M, N. So it is just a formal way to write these Fourier bases. Great. Okay, so we have already talked about the correctness of Hoare triple. Now the next question is how to verify the correctness. Here we have a set of proof rules that tells you how to derive new Hoare triples. And if you can prove some Hoare triple, finally we will prove a theorem for the soundness and relative completeness of our proof system. So that means everything you can derive is correct. So what are these proof rules? Let's start with the simplest one, the rule for the unitary gauge statement. So this rule simply says, starting with any classical states satisfying any classical conditions. And if we start with the classical, the quantum state kit phi, after executing these unitary statements, the state just satisfies this condition. So it is just applying this unitary U on this quantum state kit phi. And the second rule is called sequential composition. So it allows you to prove a Hoare triple for a sequential composition of two statements by combining the Hoare triples for each of C1 and C2. So this sequential composition is exactly the same as a classical, the classical counterpart. So here we require the post condition for the first Hoare triple to be identical to the precondition of the second Hoare triple. So in this case, we can just combine these two Hoare triple to prove a new Hoare triple for the composition of C1 and C2. So here is a quantum one, again, for the QF statement. So this rule says if you want to prove some Hoare triple for the QF statement, for this whole QF statement, you can use the Hoare triples that specify the correctness for each of the statements in the two quantum branches. So if we have Hoare triples for each CI, then we can combine them in superposition into, in superposition of these quantum states, but the classical conditions are the same. Then we can combine them into a new Hoare triple for the whole QF statements. We also have other rules for other statements. So here we have this block rule for proving the Hoare triple for block statements. And we also have this instantiation rule for proving the Hoare triple for the procedure call. I will talk a bit about this instantiation rule. So it is very intuitive. If you have a Hoare triple about the procedure called P X bar, then you can substitute this X bar by a list of expression T bar. You can just obtain this by reassigning this X bar in the classical and quantum pre and post conditions. Of course, with some additional premises. Okay, in the following, I will give you an example of how to use these proof rules to prove the correctness of quantum recursive programs. But before that, okay, there's a final rule for the quantum recursion. So we haven't talked about the rule for the quantum for the recursion. So this rule is just adapted from the classical Scott induction rule introduced by Dana Scott for proving the correctness of the classical recursive programs. And it is essentially a form of mathematical induction. So here we need to introduce a notion of provability. That means if this Hoare triple can prove this Hoare triple, that means you can use the proof rules presented in the last several pages to derive the second Hoare triple step by step from the former Hoare triples. And it should be distinguished from the correctness notation. which means whether a Hoare triple is true or false. So the correctness is defined based on the semantics, while the provability is based on the proof rule. And this recursion rule just says, if you have a procedure declaration, PU bar, then you can prove this by a form of mathematical induction. You assume you just assume this procedure call is correct. And this is your induction hypothesis. And if you can do one step of induction step, you can derive a new Hoare triple for by substituting the formal parameters U bar by these actual parameters T bar, then you execute the procedure body. If you can do this induction step, then this Hoare triple for recursive procedure call is correct. Okay, so there is something in the chat. What is PU here? Okay, PU here is the procedure declaration. So remember, our program will be a set of procedure declaration. So that procedure declaration defines this procedure P, where U is the formal parameters. So we can go back to the QFT example. So here, this whole part is the procedure declaration. So on the left-hand side is the procedure name QFT and its classical variables M and N. And on the right-hand side is C, that the procedure body that defines this procedure. So this is just a PU, and this is the PT bar. So T bar can be a list of expressions. Does this answer your questions? Okay. Okay. Thanks for this question. I will continue. So for this proof system, we can actually show that it is sound and relatively complete. So what does this mean? We have these two theorems. So the soundness theorem, intuitively it says every provable Hoare triple is correct. That means if you can derive some Hoare triple using the proof system we given in the last several pages, then this Hoare triple should be correct in semantics. And the relative completeness theorem says every correct Hoare triple is provable. Of course, this is relative, so it should be provided that true classical assertions are provable. So these two theorems promises our proof system is useful. So everything you can prove is correct, and every correct thing can be proved in this proof system relatively. Now I will give you an example of how we can prove the correctness of a quantum recursive program. So this one is very simple. It is just a program that describes a multi-controlled unitary gate. As shown on the left-hand side, this is a quantum circuit for this multi-controlled unitary U. So it's just a generalization of the one-bit control U. So for this quantum circuit, if all of the control qubits are in state kit 1, it will apply a unitary to the last qubit being controlled. And if any of the control qubit is in state kit 0, you just do nothing. So here we have this program in RQC++ that describes this quantum circuit. And we have quantum recursion here because we have this QF rule. And in one of the quantum branch, we will call the procedure C star U itself with different classical parameters. So intuitively, it roughly says if M equals to N, then there is no control qubits. You can just apply the unitary U on the last qubit being controlled. Otherwise, we need to check each of the control qubits. In the quantum way, you need to condition on the control qubit. If it is kit 0, you just do nothing. If it is kit 1, then you call the procedure itself with M+1. So you are checking the next control qubit. And this condition is in the superposition. Okay, so we can specify the correctness of this program by the following two Hall triple, which exactly defines what a multi-control gate does. So the first Hall triple, here we have this condition, which roughly says if all of the control qubits, they are in state kit 1, then after executing this C star U, we will end in some quantum state kit psi, and this kit psi is just applying the unitary U on the last qubits. And the second Hall triple just say otherwise, if any of the control qubit, if there exists one control qubit being in state kit 0, then you just do nothing. So here, quantum post state is equal to the quantum pre-state. Okay, for simplicity, in the following, I will only show you how to prove the first Hall triple. And here is an overview of the proof. So the basic idea is using the recursion rule. So remember, if you want to prove a recursive procedure call, we need some induction hypothesis. So we first assume Hall triple for this target procedure. So this is our target Hall triple. We want to derive this Hall triple using the set of proof rules. So this is our target. And if we apply the recursion rule, we can first assume the correctness of this Hall triple. Then we will use the instantiation rule to replace the formal parameters here by another parameters m plus 1. Then we can obtain a Hall triple for this statement. Then we just construct step by step to obtain a Hall triple for this whole Q statement, then to this if then else statement, and finally we will obtain a Hall triple for the procedure body. And finally, using the recursion rule, we can prove this. So here is an overview, and there are some steps omitted. So the idea is we first assume this, you can think of it as induction hypothesis. We just assume the target Hall triple is correct. Then we use the instantiation rule, which instantiate this variable m. You replace it by m plus 1. So you obtain a Hall triple like this one. Then you apply the QF rule to obtain a Hall triple for the QF statement. That is the pink block here. And then you apply the gate rule to obtain a Hall triple for the unitary gate. That is the statement here. Then you apply the if rule, which is not presented in last several pages. You obtain a Hall triple for the whole if then else statement. And finally, we will use the block rule to introduce the local variables. And using the recursion rule, we can prove a Hall triple for our target Hall triple. So here I omit some of the details, but the overall idea is using repeatedly applying these proof rules to derive new Hall triple from old one. And finally, by the soundness theorem about our proof theorem, if you can derive this Hall triple, then it is correct in semantics. So this ends the first part of today's talk. Now we will move on to the implementation part. So for the implementation, I will talk about the first is an architecture called quantum register machine together with an instruction set QINs that support quantum recursion at the instruction level. So it supports quantum control flow and the recursive procedure call. So it is just like a classical instruction set. And based on this, we propose a comprehensive implementation process of quantum recursive program written in RQC++. So suppose you already write a program in RQC++, then we can compile it into these low-level instructions, QINs. And the compiled program is not ready to be executed. We need to first perform a partial evaluation of quantum control flow information in the compiled program. And this information will be used to aid the execution of the compiled program. And final step is an execution on the quantum register machine. And this implementation is actually efficient, that it even offers some bonus. So we can obtain some automatic parallelization of quantum algorithms. For certain quantum subroutine, this automatic parallelization even provides an exponential parallel speedup for some quantum subroutine over the straightforward implementation. So let's start with the architecture, quantum register machine. So just like a classical CPU, quantum register machine operates on registers and memory. So here registers are quantum, consist of user registers and system register. And the memory is a quantum random access memory, abbreviated as QRAM. You can think of it as a quantum version of the classical RAM, but it allows the data and the address to be quantum. So the QRAM, we will divide it into several sections, just like the classical RAM. And the quantum register machine, each time they will fetch instructions from the program section of this QRAM, then it will decode and execute each of these instructions cycle by cycle. Now, remember, our ultimate goal is to tackle the implementation of quantum recursion. So we need to handle the two programming features. The first is quantum control flow, and the second is recursive procedure call. So to handle quantum control flow at the instruction level, this is inspired by the previous work, YVC24, with ideas from classical reversible architectures. The idea is we can put the program counter into a quantum register PC. And this program counter will point to the current instruction being executed in the program section. And as a quantum register, it can be in the superposition state. If you meet a QIF statement, which creates two quantum branches in the high-level language, then when you translate it, when you compile it to the low-level instructions, it will incur a superposition in the program counter. But compared to existing work, the challenge here, in our case, for quantum recursion, is how to automatically handle the synchronization problem, which we have mentioned before. It roughly says, if a QIF statement creates two quantum branches, and each of the quantum branch can take different numbers of instruction cycles to terminate. So if you want to implement the whole QIF statement together in superposition, then you have to synchronize these two quantum branches. And the picture will become more complicated when you consider recursion, because recursion will introduce non-deterministic number of nested procedure calls. So to automatically handle this problem, existing techniques are not enough. So we introduced the partial evaluation of quantum control flows, which just records the history of all quantum branching. And we store it into a data structure called QIF table, which will be loaded into the QRAM during the execution and aid the execution of the compiled program. We also designed several system registers and corresponding mechanisms for this to be done. Now for the recursive procedure call, this is relatively simpler. We just allocate the call stack in the QRAM, like how we handle the recursive procedure call in the classical case. One thing to note for our quantum register machine is the all storage components of this architecture are quantum. So all registers and the QRAM can be in a large quantum superposition state, and they can be entangled. So this is different from most of the hardware level architecture. Here, our architecture is more like a software level. So here is the instruction set, QuCS. We have 22 instructions, and most of them are adapted from the classical reversible architectures. But to handle quantum recursion, we need to introduce some new instructions. So here we have these two instructions, which corresponds to the beginning and ending of a QF statement in the high-level RQC++. And these two instructions are used to handle the quantum control flow. And we also have these two instructions for quantum unitary gates. And these instructions can be categorized into 3 types according to their format. And using this format, we can describe the decoding unitary for decode and execute the instructions. This decoding unitary will be independent on the program input. So it is fixed. And during the final execution, this decoding unitary will be used as part of the final unitary implementing the execution. So at each cycle, you apply this decoding unitary. You apply this fixed unitary. Okay, so we can talk about the implementation now. It consists of 3 parts. First, the compilation, then the partial evaluation, and finally the execution. So for the compilation, we need to compile a program in RQC++ to the QuCS. And we introduce a mid-level language, which is just a simplified QuCS. It has 3 passes. The first is a high-level transformation within the high-level language, and then we translate it to the mid-level, and then to the low-level. And this compilation is, of course, independent of the program inputs. I will briefly introduce the target for each process. So for the high-level transformation, the target is to simplify the automatic uncomputation in later process. So why we need uncomputation? Because we have classical variables. And remember, the operations, the assignment on classical variables, they are irreversible. So we have to make it reversible because we want to use a quantum unitary to implement everything. So we need to make it reversible by introducing some garbage data. And this garbage data has to be properly uncomputed during the execution. The target of the second pass is roughly translate the high-level statements to low-level instructions. And the third pass majorly handles the memory allocation of classical and quantum variables. So here is an example illustrating how the compilation works. And we focus on the high to mid-level translation. So this example program is for implementing a widely used subroutine called quantum multiplexer. On the left-hand side is a program after the high-level transformation. On the right-hand side is a high to mid-level translation of the procedure PKX. So here, we just translate each part of this statement into instructions. For example, we have these formal parameters, and we need to handle the initialization of these parameters. So they are translated into instructions. And here we also have, we need to uncompute these initializations because we want everything reversible. So it can be implemented by unitary. And we also have the assignments of classical variables. We will introduce some garbage data. Here are W1 to W2 and W3, and they should be uncomputed at the end of the procedure body. And we also have the quantum if statement and into 2 quantum branches, and each of the branches has a procedure call. That's only an overview of this compilation. Now, I will move on to the partial evaluation. So remember, our target is to automatically handle the synchronization problem, which roughly says you want to synchronize 2 quantum branches that takes different numbers of instruction cycles to terminate. So the idea is simple. You just let one of the quantum branch to wait for the other for some number of instruction cycles. But how do you know how many numbers of instruction cycles you need to wait? So the difficulty here is exactly because the recursion will introduce non-deterministic numbers of nested procedure calls. So a procedure can call itself unboundedly, depending on some condition. So our solution here is use partial evaluation. So given classical inputs, but without quantum inputs, that's why it is called partial. And a practical time T-prac, we can partially evaluate the quantum control flow information within this practical time and store all the information into a data structure called QF table. So the practical time here is necessary because we allow recursion and while loop, so it can contain some undecidable problems. So what is a QF table? It records all histories of quantum branching. And it consists of nodes and links. Each black node in this QF table corresponds to an instantiation of the QF statement. So for example, here we have this example program. When you enter the main procedure, you meet two sequential QF statements. So they correspond to node V0 and V1. They are sequential, connected by this link next. And then for V0, it has a QF that creates two quantum branch. And on the left branch, we call another procedure. And when we enter this procedure, we will meet another two QF statements sequentially. So they correspond to nodes V2 and V3. And for V3, we also have a two quantum branch and have a recursive procedure call to P itself. So again, we will enter P with n-1 parameter and meet these two quantum branch, these two QF statement again. So this will create another two nodes V4 and V5. So these links just represent a nesting or sequential relation between these QF statements. And we also have some white nodes. They are ancillary node for this QF table to be reversibly implemented. Because remember, our final goal is during the execution, we will apply a unitary that implements the compiled program with the aid of the QF table. So the QF table will be used in superposition. And we also need a counter W at each black node that stores the number of instruction cycles to wait at the current node. So we have a quantum register called QFV. It will point to one node in this QF table, and it can be in a superposition because we have quantum control flow. And if it has two branches, we need one of the branches to wait for the other to address the synchronization problem. So one of the branch can read information from this QF table and know how many numbers of instruction cycles it needs to wait. Okay, finally, the execution, we can load everything into the QRAN. And the implementation is just a large unitary, which is applying the same unitary UPsych for each cycle. And in each cycle, we will first need to check whether we need to wait at the current instruction cycle using the information from the QF table to address the synchronization problem. If we do not need to wait, we can execute. So we can apply this subroutine UX, and it consists of several stages, just like the classical CPU. You first fetch instructions, then you decode and execute it, then you unfetch because you want to be reversible, then you deal with the branching instructions. And here, the decoding unitary is exactly the one we introduced the the instruction set. And it can be implemented by elementary 1 and 2 qubit gates. Okay, so this is the implementation, and it is even efficient. It can provide some automatic parallelization of quantum algorithms. So here is an example of quantum multiplexer, whose unitary can be described in this way. So it's just conditional on the first several qubits, you apply the unitary UX. And a straightforward way to implement this unitary is you sequentially apply this controlled UX. And this will take time proportional to the sum of all Tx, where each Tx corresponds to the time for executing Ux. Now, if you use our quantum recursive programs, you can first write a program in QuCS to describe this quantum multiplexer. Then you use the quantum register machine to compile it and execute it. And this provides a new an implementation with circuit depths roughly proportional to the maximum of Tx. So this will be exponentially better than the straightforward implementation, although it is slightly worse than the manual design. But after all, this parallelization is automatic, and it can save the time and efforts for the quantum programmer. Okay, so great. So the take-home message is quantum recursive programming can be win-win. It can achieve the goal of convenient description of quantum algorithms, and it can be efficiently implemented. And of course, you can verify the correctness of quantum recursive programs. So you can try it in the design of quantum algorithms and protocols. There are several future topics. First is about the software implementation of the proof system and the implementation. And we can also consider extending the features of the high-level programming languages. And there are a lot of optimization opportunities in the compilation, partial evaluation, and execution. And we can also try to verify the compiler for the quantum register machine. Okay, this ends today's talk. Thank you all for attending.
Yeah, thanks for kind of interesting lecture today. And if there's any questions from audience, feel free to open your mic, unmute yourself, or type your question in the chat box.
Well, thank you for, can you hear me?
Yeah, I can hear you.
All right. Thanks for this very, very interesting seminar. Just it's very inspiring to see the idea that at least I never seen somewhere else before. But anyway, I do have a question. I don't have a lot of like programming language background, so I have to commit that I'm a bit lost when it comes to the proofs. But one question is, given that conditionals can be in the superposition state, how do you know when all states has reached the termination when you're doing the recursion?
Oh, okay. Thank you for your great question. So the question is about how do you know the when the quantum branches created by the Q statement will terminate? That's actually a question about the termination of program. So there is the same problem in classical programming languages because you allow recursion and while loops. So that might contain some undecidable problem. So theoretically, you cannot determine the termination before executing the programs. But here, we set a practical time T-preg. So that means you can check whether this program terminates within this practical time. And the partial evaluation part, actually, we do not need to care about the quantum input. So this check whether the program terminates is just by looking at the classical input. Then we neglect all of the quantum input. So this check is necessarily the same as the classical cases. So if you want to check termination, then this is inevitable. Does this answer your questions?
Yeah, I think it does. All right, thank you.
Thank you.
Cool. Any more questions? Yeah, I actually do have one question. So I'm actually looking to the QRAM recently, just beginning, and I understand QRAM. So the the memory part is still the classical memory, right? It's not
the
actually
memory part can actually also be quantum.
Okay.
Yeah.
I see. But based on my previous understanding, I saw many papers mentioned like the memory part, they are using the classical memory, classical registers, and QRAM is basically using as an interface or bridge, like return those like quantum information with the classical memory. And in that case, I'm just thinking about like if like multi QPUs could be linked on like those like same memory and based on this QRAM framework. And I believe you also mentions those QRAMs can probably also entangle them together, right?
Yeah, good question. So first I need to clarify that technically you cannot use a QRAM to bridge real classical memory. So those both you mentioned that use classical memory, that means in each of the computational bases, it is classical. So in some algorithm application, you are thinking like in each of the quantum branch, you can think of the memory as you can have a classical interpretation of that memory, but in general it can be also quantum. Yeah,
okay.
and to implement the QRAM, so you cannot just use a classical RAM. You need to if you want to implement a hardware level support for QRAM, it is actually technically hard in the near term. But we can have a circuit, quantum circuit that like simulate or implement that QRAM. So that is more theoretically feasible. And as you also mentioned, you are considering a scenario where there are a lot of QPU interacting on the same QRAM. Do you mean that?
I mean, kind of like build up a distributed quantum system based on the QRAM.
Yeah. That's definitely an interesting topic, but I'm not sure whether it is compatible with our current framework of quantum recursive program, because each of the QPU, they will have quantum branches, and it's complicated to imagine that you have different QPU, each has their quantum branches, and they might be interleaved by the concurrent execution of this QPU.
I see. Interesting. Yeah, thank you so much.
Thank you for this opportunity to for me to have a talk here.
I mean, you're offering a pretty interesting topic.
Yeah.
Yeah, any more questions from audience? If there's no more questions, we can probably end up today. And thanks again for today's speaker, Zhicheng, for such an interesting topic. And hope to see you guys in next lecture. Have a great day. Bye-bye.
Thank you. Have a great day. Bye-bye.